Here I'm going to discuss the material derivative. So what is the material derivative, and why do we need yet another derivative? So, but before I discuss this, let me give you the definition of the material derivative. So let's assume that we have a flow u, and our velocity field is a function of the position vector and time. So let's say that we have a quantity, we'll call it psi, but you could give it any other name. Consider a field psi, which is also a function of x and t. Note that here, when I write this, I mean these are independent variables. Now when I say consider a field here, I'm writing this as a scalar field, but it could also be a vector field. Then we define the material derivative. We write it as capital D, capital dt of psi at x and t. That is the quantity which is equal to the derivative that we already know, which is the partial derivative with respect to time of psi at x and t, plus u dot grad of psi at x of t. Now before we derive this expression and see where it comes from, we need to discuss and to understand why we need the material derivative. We need to discuss two different ways of looking at the quantity, which is the Eulerian and the Lagrangian point of view. Alright, so let's say we're looking at a particular quantity, and I'll call this quantity psi. So I'll give it a generic name, but think this psi could be pressure, it could be temperature, it could be density, or it could be even a vector field. It could be the velocity field. Right? So I'll use psi, but it could be anything. Now, how can we describe how this field, how psi varies? Well, there is a first way of looking at it. That's the Eulerian point of view. Now let's think here. Let's assume that we have flow. I'll just represent flow with these. These are neither streamlines nor particle path line. It's just a way of representing flow. But let's think about a flow which is unsteady. Now one way to look at the variation of psi, so how psi changes with time, and then if you looked at your quantity and how it varies with time, this quantity could be temperature, for example. So your temperature probe, your thermometer, would give you the variation of the temperature. So you would record as a function of time your field, your temperature here, and you may record an increase, decrease, increase of temperature. And all of this is at a fixed position x0. So how mathematically can we describe the variation of this function at a given x0? Well, this is exactly the definition of a derivative which you already know about, and that is the partial derivative with respect to t. So in this case, the variation of psi are represented by the partial derivative. Right, remember, so that would be partial psi over partial t at x equal x0. So we're holding all of the other independent variable x, y, and z. So the position we're holding fixed. When we look at this partial, when we look at the variation of the function psi in this way, that is the Eulerian point of view. Now there is another point of view, and that is the Lagrangian point of view. So here again, let me represent the flow, and the Lagrangian point of view is another way to look at the variation of psi, but this time not at a fixed location, but this time we look at the change of psi when we follow a material element. Follow a material. Now what does that mean? Well, that means that we look here at a piece of the fluid, right? So the piece, this fluid element here is at a certain location x at a certain time t, right? And the value of psi here is psi at x and t. And then because there is flow, this piece, this material element of fluid, so the molecules, the air, which is the air or the water, which is here, is going to move, is going to be transported. At a later time t plus delta t, it will have moved to say here. That is the location of the same material at a later time. So at time t plus delta t, it will have moved to the location x, let's say, plus delta x. Delta x would be this displacement here. And so we may be interested in now, how has psi changed? So what it has changed by delta psi. What is this change of psi as we followed a material element? Now, if in this case, we look at the variation of psi in time, and these are represented mathematically by the material derivative. Now, why is the material derivative important? So, the partial derivative here, right, is the easy derivative to compute when we have a function of several independent variables. So remember, psi here is a function of independent variables of x and t. And so the Eulerian point of view, computing this partial derivative, is what is easy to do. But physically, really, when we look at conservation of a quantity, the derivative which is mostly related to conservation principle is the material derivative. Let me explain. Assume you have heated a patch of air here. You've heated this patch of air, and now this air is transported. So this patch of hot air is going to move slowly along the flow. If you're looking at the Eulerian perspective, then you stick your probe here. Right now the temperature is low and the patch of air is slowly coming. And at some point the temperature is going to rise because the hot air is coming through, and then it's going to decay. That's if you look at it this way, it's hard to just see where the conservation comes from, because the temperature just changes, and you're not always measuring the temperature of the same material element. In that case, it's different. If you're looking at heating this element, right, and then you follow this element, then the changes of temperature are going to be much more less drastic. There might be some diffusion, you might dissipate some of this temperature, but all in all, this derivative, you're looking at the variation of temperature then as you follow a material element, that is most closely related to the conservation of energy. So this is why you will often see in the governing equation the material derivative appear. Okay, so we'll continue by deriving the expression for the material derivative. So here it will have helped if you have watched the reminder of multivariable calculus, and in particular the little video on partial differential equation. On partial differentials. Partial derivatives. So to derive the material derivative,